Okay. Today we are going to see about the industrial robot modeling with a mathematical approach. In this mathematical approach, we are going to see how the kinematics and the dynamics of the rigid body of the robot could be represented in space and in time. So, what is the time representation and the space representation of this kinematics and the dynamic models? In general, just for a revision, maybe you have studied in different lectures or in different courses about the position, about orientation, about rotational matrices, about coordinate systems, how to represent a vector, how to represent them Euler angles, quaternion units, and also about the homogeneous transformation matrix. Also, you might have seen about spatial vector notation. What about canonical equations? How do we have a forward kinematic model and the inverse kinematic model? And also, I believe you could have heard at least about the dynamic models of rigid bodies, maybe in machine designs or maybe in dynamics or something like that. So the other is in dynamics, what are the modeling techniques? In general, actually, there could be about 3-4 approaches, like Lagrangian method, about maybe like Newton-Euler method, or about bond graph or something like that. But that is not really our concern. We are really interested in the Lagrangian approach and the Newton-Euler approach. The bond graph approach is maybe not really useful for us. Maybe we could have, in future, maybe we could have a look to that. So, okay. The other point is whenever we talk about this rigid bodies, because a robot is a rigid body, we can talk about the description of these rigid bodies in terms of 4 parameters. These 4 parameters in robotics, we call it a Dynamit-Hardenberg notations. These are link lengths, joint angle, offset angle, and offset lengths. Actually, we are going to see this in detail later on. But whatever it is, if you have a rigid body in the space, you need a position representation and the orientation representation. So how do we represent the position and orientation of the rigid body in the space? That's really a big question. And that's also really a main topic in the robotics. So how do we represent this position of a joint and a link in the space? So we have 2 things. One is joint, the second is a link. So how do we represent this link and the joints in the space? Then how do we really precisely know the position and the orientation of these joints and the links? That's a question that motivates us to learn about robots. So in general, whenever you think about rigid body, it's an object, it's a body which doesn't deform or which doesn't make a change of position before and after a force is applied. So that is a rigid body. So we assume a link is a rigid body. That means it doesn't deform under applied force. It will retain its original shape and its original position. As a result, the body doesn't affect the kinematics and dynamics. So we are only interested to know the position of the joints and the rotation of the joints with respect to this kinematic change. So that's our preliminary assumption. So we say a robot, industrial robot that we are using nowadays in this application will be considered as a rigid body, even though there are soft robots which are really in contrast to this assumption. But soft robots are really rarely applied in industrial application, and also we are not going to discuss about that. But we consider the robot body is a rigid body. It is fixed. It has a fixed shape and a position at particular time. So in general, in a robot, we can have either an object, or we can have either tools, or we have parts, or maybe the robot itself. So there is a robot body, there is a gripper attached to the robot, which we call it a tool, and then also we could have parts or objects that are going to be manipulated or to be picked and placed. So in general, position, we said there are two entities. One is position, and the second is orientation. So how do we represent the position, and how do we represent the orientation? These are the two questions. Position is, it's a representation. It can be represented with a vector, which is a position along x, a position along y, and a position along z. Similarly, orientation can be represented by a matrix of 3 by 3, which can be a orientation along the x-axis, along y-axis, and along z-axis. So in general, whenever you have a position of an object, if you have a rigid body, something like this could be represented with a position of the rigid body. Maybe we can consider a particle on the rigid body where we want to analyze. So maybe we can have 3 pointers here. So these are the 3 pointers. Now this point can be represented, this object in general can be represented in the space with the Cartesian coordinate system. With the Cartesian coordinate system, we can represent it like x, y, like x, y, and z. This x, y, z of the rigid body can be, now for this one we have a position. Maybe we can write it something like this. We have a position of this point from O, and we have a position of this point from O, and we have a position of the third point. So third point from this, So we have the 3 points. Now these positions have, for example, P1 has angles from x, it has angle from y, and also it has angle from z. Maybe we can say alpha, beta, gamma. I think you have this concept maybe from different courses. But the question is, the position of an object, a point, maybe for example, P1 can be represented as position of 1 along x-axis. We can say P1x, this position along y-axis, which we call it P1y, and it can be decomposed into or projected into z-axis, which we call it P1z. So P1 in general can be represented as Px, P1x, P1y, and P1z. So this is a vector. This is a vector. As I said, there is this point has a orientation about x-axis, about y-axis, and about z-axis. This orientation of 1 can be given as a rotation about x, a rotation about y, a rotation about z. The rotation projected along y, along x, and along z. Okay, so if you consider only rotation about x, orientation about x, P1 along x can be P1 cos alpha, sine alpha, and 0 alpha, because alpha along alpha, P1 can be cos alpha and sine alpha, only because it's in the space, So here you have rotation about x means alpha, rotation about y can be beta, and rotation about z can be gamma. So just there are rotations. So this P1 can be rotated about x-axis, about y-axis, and the z-axis with the alpha, beta, gamma angles respectively. Yeah, but just this is in general. So now let us use this concept in robotics. Let us use this concept in robotics. Whenever we use this concept, if we apply this concept, you know, assume you have a robot as we usually do. Something. Just do something like this. So for this particular example, we could have rotation about this, rotation about this, rotation about this. So we have the first rotation is it rotates about this axis, others are this. So now the approach is first we have to assign the reference frame. Okay. So whenever you have a rigid body, so you start from defining the reference frames. So first you do define your reference frame. So I will tell you now the convention, how to define the reference frame. So whenever you attempt to define a reference frame, z-axis is always along the rotation axis, along the rotation axis of the joint. Along the rotation axis of the joint. For example, if you have a joint, something like this, if you have something like this, and if it rotates about this axis, you know, the rotation axis is, this is a rotation axis. This is a rotation axis. This rotation axis is always, okay, it is Z. It is always Z axis. Axis of rotation is always Z axis. So with this convention, okay, so let us assign Z axis. So this is rotating about this, so I will assign this Z axis. Z of the first, maybe we can say Z1. Z1. Now this is perpendicular to the screen. Perpendicular to the screen, maybe I could assign something like this out of the screen. Z2. Then this is also is perpendicular to the screen, so I will assign Z axis outside the screen as Z3. So always Z is along axis of rotation. Z is along the axis of rotation. It is always along the axis of rotation. Okay, rule 1. So this is rule 1. What about rule 2? Rule 2 says assign x-axis along the axis, along the link axis, so link axis. So assign along the link axis. This is the second step. What is link axis? What's link axis? Link axis means, for example, for Z2, the link of rotation, the link that is going to be rotated about Z2 is this axis. For Z3, the link that is going to rotate about Z3 is x3. Okay, so it is along the axis of rotation. This means also, you know, you have a freedom to choose x2 because link, for example, this link is variable. I mean, this x2 can be sometimes along the at this position, or it can be also at this position. You know, whether I assign exactly here or here, more or less it is similar. It's similar because this link can move up and down. It can move up and down. So if you assign also x2 like this, you got right answer. Okay, so that's completely right. If you assign like this also, it's completely right. Because for the first joint, you know, you have freedom to select the x-axis along your desired, you know, for example, because there is no link, you know, for joint 1, so I could say x1 is here. So to simplify, you know, because I'm going to apply some trigonometric relationships, so I would like to simplify as much as possible. So how do I simplify? At least for the visualization, I would simplify. I will assign x1, x2, and x3 parallel to each other. So this time, at least I can easily visualize, right? So I can easily understand how the links are interconnected and how they are going to be kinematically manipulated. So I would prefer, personally, I would prefer to make them parallel. So it's easy for me to understand, you know, what's going on. Just even to derive the mathematical relationships, it will not be that much complicated. So for me, I would like to assign just parallel to each other to avoid as much as possible an offset angle of rotation, just an offset angle. So that's the second thing. And the third point is actually maybe before that, you assign the axis and the x-axis. Yes, we said, but how do you know the direction? Use your right hand rule. Okay, with the right hand rule, if you grasp, for example, this object, you know, with your 4 fingers, the thumb finger will direct to this direction. This is your thumb. Then here is your thumb, and then you have other fingers grasping here. Something like this, you know. So you are grasping there, and so it is clear that the direction of the axis here. The same is true here. Put your hand like just put your hands like this, fingers like here. You know, put like this. Then here, you know, there is an object. So this is axis of rotation. So it is rotating about this axis. Then your thumbnail is directing up. So this is positive z-axis. This is positive z-axis. So this way you can decide for the direction. The third question is about y-axis. How do you define y-axis? As we said, use right hand rule. Right hand rule. Just fulfill with the third axis could be fulfilled by the right hand rule. So we don't care, we use the right hand rule. If I assign x-axis about this, y-axis about z-axis about this, the right hand rule shows y-axis is this one. If I have x along this, z along this, the right hand rule tells me this is y2. If x3 is like this, then it is almost parallel. I have y3 here. This is the main requirement, and actually this is the first step, and it could be also the main requirement for correctly assigning the reference frames for your robot links and joints, for your robot joints, main, of course. If you fail here, then you will fail in the remaining sections, because if you cannot really properly assign your reference frame, the motion that you are going to get from the kinematics is completely sick. It doesn't provide you really an accurate solution. So if you fail here, the remaining solutions are also wrong. So just you have to pay attention to accurately define your reference frame at the very beginning. So just these are the three rules. First, assign the axis along the axis of rotation or along the joint actuator, or it is the rotation of the motor. So in which axis is the motor is rotating. Then x-axis is going to be assigned along the link axis, but the link axis, as we said, it could be variable. So you can have here a freedom to align the x-axis with the previous joint axis in order to avoid some kind of offsets or joint offsets. Yeah, so as much as possible, actually, if you try to make the first joint and the second joint similar in the similar orientation, actually, at least in the similar orientation, it makes really it really simplifies your problem. Otherwise, you could have some joint offsets and link offset as well. So just try to consider this. Okay, so this is the first step. So we start from assigning reference frames. Is there any question? Is it clear for all of you here? Okay, it looks like you all are okay with this. Okay, so now the second step is, if we got a reference frame, then how do we represent the spatial representation of the position and orientation? That's the next question. So we have a link. Now let's say assume this is our first link. Now let us start from the scratch, just to understand. We said we assigned this one as x1, this way y1, and this way z1. Okay, that's good. Then maybe also we can assign this one. I say this is x2. Maybe this is y2, and perpendicular to is z2. Now let us physically try to understand. x1 and x2 are parallel. There is no offset. There is no any angle offset between x1 and x2. Between x1 and x2, the angle change, the angular change between x1 and x2 is 0. The angular change, the change of angle between x1 and x2 is 0. The change of angle between y1 and y2 is between y1 and y2 is how
90.
much is that? 90, definitely.
90 degree.
Positive or negative?
Negative.
From 1 to 2. From 1 to 2.
Negative.
Maybe the
Negative.
why you say negative?
Clockwise
As
rotation.
it is anti-clockwise rotation
It's,
from y1 to y2.
oh, it's positive. It's positive, sir. It's positive.
Yeah, it's positive. It's positive because we are rotating about x-axis, right? So
We
it's
got
Yeah,
positive.
anti-clockwise
and-
rotation about X.
Yeah. Okay, good, great. The third one is the angle between the change of angle between Z1 and Z2 is it's also 90, right?
90 degrees.
Yeah.
Okay. Now the angle, those angles, these angles are offset. So between y1 and the y2 and the z1 and the z2, there is offset angle. So we call it offset angle. It is offset angle. The rotation about z-axis, which we call it theta 1 here, and then we call theta 2 here, is called, we can assign this one alpha. And theta is theta, which could be theta 1, theta 2 is joint angle. It is a motor, it's a motor rotation also. It's a joint angle, or it can be rotation, joint rotation. You can say also joint rotation, or you can say actuation. It is motor, it's actuator motion, or just the actuator's rotation or something like that, or the actuator position. That Okay. Now the distance between the first link joint and the second joint, between this and this, we call it this, we may call this one link. Yeah, so we may call it link length. And the distance between the next here also, we can call it the link length. And so on. Yeah, so that's not again our main question, but here again what I want to emphasize is how to assign our rotational and positional vectors in the matrix. So from just maybe I can start from a simple revision again. If you rotate this object about this axis, it could be here. Then again, also if you continue rotating, it could be here. And so on, right? So it can be here, it can be here, if you rotate it in negative direction, of course. Now the question is, if you are here initially, and if you come to this position after some time, there is theta, delta theta, between these two, between this and this pointers, there is delta theta. There is delta theta. Okay, so now from I think from the physics, if you have this one as y-axis is of x-axis and perpendicular to z-axis. And if you have link 1 here, this could be decomposed into L1 cos of delta theta, and this can be decomposed as L1 sine of delta theta, something like that, right? From the physics. Then L1 in general can be represented as L1 cos delta theta. L1 could be L1 cos delta theta 1 plus L1 along I, L1 delta cos, no, sine delta theta of along J. Something like this. I think you have seen something like this, and so on. So actually, I don't care about that. But now from the rotational matrices, you know, if you extend this one from the this concept, the rotational matrix, because now we are rotating about z-axis. This is rotating about z-axis. So rotation about z-axis of this delta theta can be represented, you know, just if you derive this mathematics, it could be cos delta theta 1 minus y minus, because L1 sin theta here is minus. Actually, I can put here minus because this is down, but y is upward. You see, this is L1 cos theta is along the positive x-axis, but L1 sin theta, while it moves down, it could be L1 sin theta minus sin theta. But this delta theta is true when the delta theta is approach to 0. Otherwise, you could ask me, you know, how does this long length and this can be decomposed to something like that. But if delta theta approach to 0, we assume L1 is or more or less equals to L1 cos delta theta, and L1 0 equals to L1, maybe approximately L1 sin delta theta. This is an assumption actually. So now this could be rewritten as cos delta theta 1 sin delta theta 1 0 sin delta theta 1 cos delta theta 1 0 along z axis is only a unit vector. So this is a rotation about z axis. This is a rotation about z axis. Maybe we could further elaborate this one. The derivation, actually, if you are really a person who want to prove something, you know, you can refer further. But for us now, I think the concept could be enough. So I will say I will have rotation about z of delta theta can be, I will say C means cos, S means sine. So cos delta theta 1 minus sine delta theta 1, sine delta theta 1 cos delta theta 1 0 0 1 0 0. The second equation is rotation about y-axis. Rotation about y-axis of delta theta can be so cos delta theta 1 0 sine delta theta 1 0 1 0 minus sine delta theta 1 0 c delta theta 1. And the third one can be, I can write here. No, I could have space here. I could write Rx of delta theta can be written as 1 1, 0, 0, 0, cos delta theta 1, sin delta theta 1, sin delta theta 1, cos delta theta 1, 0. Yeah, maybe I could miss positive minus something. We can check that one. But the concept is, what does rotation about z means? So we are rotating about z axis. So this is unit vector. So rotation about z is 1 here means it is rotating about z. Rotating about y axis means, you know, the y component will be unit. Then when you rotate about y, you have a decomposition about theta, about x and about y only, about z only, x and about z only. When you rotate about z, you have only rotation about x and about y only. The third is when you rotate about x axis, you have only a rotation, you have a decomposition of this or projection of this rotation into y and z only. That is what we have seen here. For example, you know, if you remember here, this from 1 to 2, from, you know, the angle between x1 and x2 is 0. Between x1 and x2 is 0, y1 and y2 is 90, z1 and z2 is 90. Why? Because this, you know, if you consider these reference frames, they are rotating about x-axis. Look, y1 to y2 means rotation about positive x. Also, z1 to z2 means rotation about x. So whenever you rotate about x-axis, you have a change of angles on y and z-axis. This is no rotation. This is no rotation. It is a unit. It remains constant. The rotation between x is constant. This is constant. But if you rotate about x-axis, you will expect a change of rotation about y and z. So this is the same is true here. The same is true here. In this situation, when we rotate about x-axis, we moved only about y-axis and the z-axis. When we rotated about y-axis, we have only rotation about the projection of this rotation into the z and the x-axis. Whenever we rotate about z-axis, of course, the projections of this rotation will be the projections of this unit vector, angles will be along x and y. So this is something that we have to know for a robot. Just, you know, so if you say rotate about x-axis, you do expect motion along y and along z. Okay. If you say move the robot along, rotate the robot along x-axis, the linear motion will be observed along z and y. If you command the robot to rotate about x-axis, no, about z-axis, you expect a motion along x and the y axis, linear translation along x and the y axis. So that's actually why we need to know these things, you know. So in simple words, actually this means you have these robots, and it's here now, and you want to move this robot, you know. So you want to move this robot as the following, you know. So you are here, but after some point you want to move it something like this. Then you want to move this just like this, and you want to move this like this. Okay. You want to move something like this. So here there is change about this. There is change about this. But this is Z axis. So this is X axis, and this is Y axis. This is Y axis. Now, in this example, when you rotate this one about this axis, actually no, it's this direction, but it is in this direction. When you rotate about this direction, it is Z axis. So the motion about this axis along Z axis is not affected. Only the motion is translating toward X and Y. There is no motion observed along the. There is no motion observed along the Z axis. The Z axis is only a pure rotation, so it's only a pure rotation. But the translationals are executed along X and Y motions. So that's what we have to. That's why we have to. Then why we have to designate a rotation and linear. In general, actually, now we said we have a rotation matrix which are 3 by 3. Rotation matrix is always 3 by 3, and they have their own properties. Actually, if you are really a person who is interested in control theory or something like that, yeah, you can check these properties. For example, if you have a rotation, about Z of theta, which is cos theta, sin theta, cos 0, 0, 1, 0, 0. The rotation matrix of Z theta inverse equals to the rotation matrix Z of theta transpose. True or false? You know, this says the transformation matrix of the inverse of the rotational matrix can be equal to the transpose of the rotational matrix. It's true. How? Just, you can prove it. Just do the inverse of the matrix and just check it with the transpose. This applies for everything for this transformation matrix. So there are so many properties like this. If you are interested, actually, you can check them. Here it is. So the rotation matrix which map joint J into I is equal. The rotation matrix which map joint J to I or joint I to J is equal to the rotation matrix which maps I to J. You know, here look it. If it is from I to J, it is equal to the inverse of J to I, or equal to the transpose. So the inverse of the rotation matrix and its transpose are equal. They are equal. So what does that mean? Yeah, that means if you have a robot here, this robot, you know, if you have a rotation matrix of this with respect to this, okay? So the 0, 1, 2, 3. The rotation matrix of 2 with respect to 1 is here, okay? Rotation matrix of 2 with respect to 1. So the rotation matrix of 2 with respect to 1 equals to, you know, this one. Okay, now I'm here. Is equals to the inverse of rotation matrix 1 with 2. That means I'm here. Okay, the second. If you invert this one, you can get here. This rotation is the inverse of this one. You know, that means this is the inverse of this one, or if you are here, then you can get here by inversing, and then it is equal to this one. Maybe if maybe here, sorry, maybe if we are assuming forward, if this is forward, the rotation matrix of 2 with respect to 1, if we assume it's forward, then if we make the inverse, you know, we are here. So rotation of this is the inverse of this one. So this is inverse, this is forward, positive, yeah, this is positive, this is inverse. And this inverse is equal with the transpose. It's equal with the transpose. So the same is true here. If you come here, you can go back by the inverse, but this inverse is equal to the transpose. That's what it means. If you are coming here forward, then you can go reverse by inverse, but it is equal to with its transpose. That means inverting a matrix is difficult, right? It's difficult, you know, it's computationally difficult. So if you have a rotation matrix, why do you do an inverse computation of 3 by 3 matrix? It's difficult, right? So instead of doing the inverse, you can make simply transpose. Just exchange the vertical and the horizontal elements, and then you get the transpose within 5 seconds. So if it appears on exam, for example, if I ask you just to do the reverse of the rotational matrix, why do you do the inverse? Just do the transpose, and then you will get the final result just within 5 minutes. No, with 5 seconds instead of 5 minutes. Okay. Then you may not complain then. Inverting a 3 by 3 matrix is difficult, something like that, because it is simple. As yeah, so this is a trick actually. Yeah, so in general, I can say a robot can be represented with a combination of the rotation and the position vectors. So we say we have now, so far we have position matrix, position vector, which is position along X, position along Y, position along Z, 3 by 1. We have rotation. We have rotation. This rotation is rotation about X, 1, X maybe, rotation about XY, rotation about XZ, rotation about YX, rotation about YY, rotation about YZ, rotation about ZX, rotation about ZY, and rotation about ZZ. pure rotation, pure rotation, pure rotation. These are hybrids, a combination of yx, zx, xy, zy, x, z, xz, yz. Now the question is, this is 3 by 1, this is 3 by 3, then maybe it's still a little bit not convenient for manipulation. Then people start to have a simplified representation, which we call it a homogeneous transformation matrix. A homogeneous transformation matrix, just homogeneous. So in homogeneous transformation matrix, also some guys actually in a computer science or something somewhere, they call it also affine transformation. Don't be surprised if you hear about someone saying affine transformation or something like that. More or less they are similar. What is it about? It is about 4 by 4 matrix, which combines positional vector and the rotational matrix together. So it says a homogeneous transformation matrix. I can represent T. T means a homogeneous transformation matrix, or I can represent A. I don't care. Or you can say H also. Then A is a homogeneous transformation matrix is rotation matrix. For example, if you consider only the Z axis, I could say rotation about Z is cos theta minus sin theta 0, 0, c theta, s theta 0, 0, 1, px, py, pz. Then if you keep this one as it is, it will be 4 by 3. 3 by 4. It will be 3 by 4. Then 3 by 4 matrix cannot be inverted because you may need to make the inverse, otherwise you may not calculate for example reverse motion, otherwise you will be always just doing the homogeneous the forward transformation matrix. So in case you are interested to make the reverse motion, you need a matrix which is square or which can be inverted, or which a matrix with full rank. But now this has not square, this matrix is not square, or it's not a full rank, so I would make 0, 0, 0, 1, just a unit. I would add a unit to make it complete, just to make it invertible, to make it full rank matrix, just nothing else, This doesn't affect your solution because it is a unit, but it helps us to invert the matrix in a right way. So that's the idea. So a homogeneous transformation matrix in general consists rotation matrix about X, rotation matrix about Y, rotation matrix about Z, and the position vectors about X, Y, Z. So this is rotation about X, rotation about Y, rotation about Z. This is position. Yeah, this is called homogeneous transformation matrix. It represents a combined position and rotation vectors and the matrices into a single matrix. So this single matrix can represent position and orientation of a single joint, one with respect to the other. So if you have a chain of kinematics, so you could have multiple homogeneous transformation matrices which are relative to each other. Then by multiplying those all matrices, you can obtain your overall matrix. So if you have, for example, if you have 6 joints, if you have 6 joints, the robot position from 0 to 6 means A0 to 1, A1 to 2, A2 to 3, A3 to 4, A4 to 5, A5 to 6. You multiply together, okay? This is a matrix multiplication. You have 6 elements. So from this, maybe someone can see here 1 kills 1, 2 kills 2, 3 kills 3, 4 kills 4, 5 kills 5. Then finally remains 6 here, 0 here, so 0 to 6. You know, so it is from 0 to 6. So A01 means a matrix with 4 by 4, comma. A1 to 0 to 2 means matrix with 4 by 4. Continues like that. So it is a matrix multiplication of 4 by 4. Then it gives you the position of the final matrix of the end effector or the tool center point. Then you can use the tool center point to calculate the position of the end effector with respect to the ground global reference frame or the base reference frame. Yeah. Then actually all the software, you know, all the softwares, of course, for example, the software that we have seen last time implements this mathematics behind, you know, in process simulator or in robot expert. This mathematics is behind to allow the robot in the effector or the tool center point to move from one position to the other. Without this mathematics, nothing will happen. So in a robotics, this is compulsory. It's a basic knowledge. This is for a robotics, a basic knowledge. Any robot model will have this function inside. The dynamics can be additional, but kinematics is compulsory for any robot. The question is, how do we do the inverse kinematics? It's nothing but you apply the same thing. If you have A0 to 6 equals to A0, 1, if you have A0 to 6 equals to A0, 1, A1, 2, A2, 3, A3, 4, A4, 5, A6, 5. Inverse matrix means, for example, you have this. From this, you want to calculate this one. You have this, but you don't know this one. So this time you have to apply inverse kinematics. So in A01 means A06 overall, A1 to 2, A2 to 3, A3 to 4, A4 to 5, A5 to 6 inverse. So you got this one. This is also available, you know, just in most. This is also a basic knowledge for a robot, so it exists on most of the robots. So yeah, we have to know this one as well. But the question: do we know this? Do we know this? Do we know this? Needs this? Maybe yes, maybe not. Yeah, this is difficult actually. Inverse kinematics. This is called inverse kinematics. Inverse. This is forward kinematics. Forward kinematics. Forward kinematics is simple, very forward. Inverse is not simple. It's inverse. It's a little bit difficult, and that has a lot of complications actually. But there are so many approaches for inverse kinematics. You can have a geometric approach, you can have a numerical approach. Even nowadays, there are guys who have tried to compute the inverse kinematics of the robot using the learning algorithms. Just they train a robot from the forward kinematics, and then they train the robot to do the inverse kinematics for each joint variables. That's possible, of course, but it is computationally demanding, and then you have to export the model with the robot anytime, So it depends on the trained model, and also it depends on how the model is accurately represented in the model. But yeah, there are people who have tried to do that. Yeah, so in general, from the practical point of view, we can have at least 3 reference frames, maybe 4. The first is a world reference frame. World reference frame is a reference frame to which you compare, So it is where you are going to compare. The other, yeah, just we have to know world reference is just where you are going to compare. It is a global reference frame. If you don't have this global reference frame, you don't have any reference. So how to which do you compare the motion of the robot? So you need a world, you need a base reference frame where you place the object, and then it will be measured with respect to the object. And the other is a tool center reference frame. It is a reference frame attached to the tool center. Actually, we have seen these things during the tutorial session. You have seen tool reference frame, the world reference frame, and so on. I think that is the best place to practice and exercise. So we don't need to go in detail actually in this one because we have seen it in the tutorial session. So if it appears on the exam, then it will be in the consideration of the tutorial session. Okay, so from this, so I can pass this one. The other one is about Euler and the quaternion space. Yeah, actually, if you know, I think for example, in the plane, you have 3 rotations: yaw motion, roll motion, and the pitch motion. Also, the same is true for cars. You have roll, pitch, and the yaw motions. The same is true for robots. We can represent the robots by yaw, roll, and the pitch, which is Euler representation. That's not a problem. But the problem of Euler is, you could have multiple solutions for a simple problem. So the question is it, you could have multiple solutions. So, for example, I don't know if you have seen here. If I do have it here, I don't know. No, I don't have it actually. So maybe I can give you some examples. A robot can achieve multiple positions. For example, you have a robot here, and this robot has this link. You could have the same solution from this direction as well. This angle. If this is 60 degrees, then this is also 60 degrees. But this is minus 30, but this is plus 30. So here minus 30 and here plus 30. And if this is maybe just let's say 60 degrees, then this will be 30 degrees, something like that. So there is a unique there is one solution. There is one solution. There is one problem. There's one problem. The problem is to achieve this position goal. But the solution can be either this one or this one. Then the robot will be confused. Okay, so shall I follow this path or shall I follow this path? The robot will be confused. In order to avoid such confusions, and also in order to avoid some kind of singularities. Singularity is where the robot has undefined solutions, which is due to the computational incapability of trigonometric functions, of course, and the link configuration as well. You have to find a way to avoid this confusion. So maybe one potential candidate is quaternion space. In quaternion space, we have a vector of 3 and one scalar, which represents the magnitude. So in general, we have 4 parameters, 3 vectors, 3 vector elements, and 1 scalar. Okay, so in general, we have a function, something like this. Function something x, y, z, w. This w is a quaternion. Actually, if your robot has multiple degree of freedom, like a humanoid robot, you have lots of links and joints. So this time, the kinematics could be a little bit difficult. In such situations, you may choose to use the quaternion space to avoid any kind of multiple solutions, or maybe some kind of singulars or something like that. But it is the same thing, but in a different representation. Quaternion is an imaginary space. It is in a complex. It uses a complex numbers, or it uses an imaginary axis. It takes from the x, y, z into a different hyperplane. But the Euler uses the Cartesian space, and then it will compute the rotation about each axis. But quaternion uses a hyperspace to represent the rotation and the magnitude. That's the difference. Actually, if you are interested, there's mathematical representations in this lecture, so you can look to that point. That's all about today's session regarding the kinematics. Next week, I will try to show you some concept about the robot dynamics, and then we will have 2 more lectures. The last 2 lectures will concentrate on the numerical control because of the automation. We will see how we can extend this motion in numerically controlled machines, like CNC or NC machines, something like that. So this is more or less overview of the kinematics theoretical background in general. So if you have any questions, I'm happy to react. And also, I would like to know your feedback regarding these topics. Just also, if somebody has better explanation, also I'm happy just if you have some experience with practical, and then if you have seen something, and then if you want to share with us, actually that's really a good opportunity for us to learn from each other.
Sir, can we know any standard textbook for the robotics, sir?
Sorry, I didn't get.
Standard textbook.
Okay, actually there are some textbooks. I already mentioned it at the very beginning. I don't know. Actually, I use the book I use for the lecture. This one is the main book I use. It is Siraj. Also, you can use Siciliano. It is
so author name, sir? Author name?
Siraj.
Okay, Siraj. Okay, sir.
Hi,
Siciliano.
Professor.
So
I would like to know if you could provide us some exercise regarding these topics of the robotics.
Actually, we will try to see in the tutorial session.